Okay, let's work through this problem. I'm going to have one electrode that I'm going to make in a galvanic cell with solid gold and aqueous gold. The others can have solid silver and aqueous silver. What's the overall reaction? What's going to be the cell potential? What's going to be the cathode? What's the anode? Diagram the cell. What all is going to happen here? All right. Well, here we go. The first question is, well, what's going to happen? Note, I have solid gold, solid silver, aqueous gold, aqueous silver. Since I'm setting it up as a galvanic cell, I know I'm going to need to use the standard electrode potentials and see what is to the right and below what, because that will tell me what reactions are happening. So here are my potentials. I need to be looking for gold 3 plus, solid gold, silver 1 plus, and solid silver. Okay, note, once you find one, you can pretty much find the other. Here's gold 3 plus, there's solid gold. Where's silver? Silver. Here's silver plus, and here's solid silver. Well, this table tells me that whatever's over here will react spontaneously what's over here and below it. So what's on this side? Au3 plus. Gold 3 plus is on the left, and it will react spontaneously with silver solid. All right. So I now know that my gold 3 plus, due to this table, Au3 plus aqueous, is going to react with solid silver because of my diagonal rule. I also know from these reactions here that the gold 3 plus is going to take 3 electrons and react to form gold solid. And my silver solid is going to react and lose 1 electron to form Ag plus. So I know I'm going to go to gold solid plus Ag plus aqueous. All right, so now there's my reaction, but is it balanced? Turns out it's not balanced because, yes, I've got 1, 1, 1, and 1, but my charges are not balanced here. So we need to balance this overall reaction. How do we do that? First, separate into the half reactions. Note, separating into half reactions is really going to help us work out the rest of this problem too. So, all right, first half reaction, Au3 plus aqueous goes to Au solid, and as we noted from our table, it's plus 3 electrons. You just read that right off the table right here. Au 3 plus 3 electrons goes to Au solid. It's almost the standard reduction potential. It's almost like cheating. And even better news, you don't have to memorize this table. It'll be given to you. So note the electrons are on the left, so we know this is reduction. And we also remember reduction happens at the cathode. So here's our reduction at the cathode. What's our oxidation? Well, our oxidation has to be this silver solid reacting to form Ag plus, aqueous silver ions. And for charges, we can see neutral, plus 1. I need 1 electron over here. That's the long way. The shortcut would be look at that table of reduction potentials, and it told you that. But recall, the next thing we need to do is even out the number of electrons, right? I've got 3 electrons on this side, 1 on this side. Can you see that we're going to have to multiply this bottom one by 3? So this is going to be 3 Ag solids plus, goes to 3 Ag plus 3 electrons. This is our oxidation, and that happens at the anode. So what is our overall reaction going to be here? Well, electrons cancel. It'll be Au3 plus aqueous plus 3 Ag solid goes to 3Ag plus aqueous plus Au solid. So there's our overall reaction. Check. Oh, what's the cathode and what's the anode? Oh, we've already got that. Here's the anode, here's the cathode. Got it. The EMF, the cell potential. Okay, if I hook this up, what's going to be the voltage going through the wire? Well, our table of standard reductions says that our gold, when it gets reduced, has a potential of positive 1.50 volts. So we know that E naught reduction here is positive 1.50 volts. When we look at silver, we see that it's got a value of 0.8 volts, but recall, this is reduction. This is our reducing the silver. This is E naught reduction. Our reaction is actually the oxidation of silver. So if the reduction has a value of 0.80 volts, the oxidation has a value of negative 0.80 volts. E naught ox equals negative 0.80 volts. Oh, but wait a minute, we had to multiply it by 3. What happens if we multiply by 3? Correct, nothing. The voltage does not change when you multiply by the stoichiometry. So the only thing we had to do is realize this was an oxidation reaction, so we just had to flip the sign of the voltage. Well, what is then going to be E naught cell here for this reaction? What's going to be our cell potential? We know E naught cell is the reduction potential plus the oxidation potential. So what is plus 1.5 plus negative 0.8? Well, that's 1.5 minus 0.8. That is 0.70 volts. Note, if you did it correct, this has to be a positive number, because if an E naught cell is a positive number, it means the reaction is spontaneous. And by doing the diagonal rule, you make sure it's a spontaneous reaction. If your reaction is following the diagonal rule, then the E naught cell will be a positive number. It will be spontaneous. Cool. That gets us our EMF cell potential is 0.70 volts. What's the diagram? Well, remember, the diagram always starts at the anode. And if we think about it, if we were to actually draw it out, now the diagram, I mean the lines for salt bridges and stuff like that. But if we were to diagram this out in terms of drawing it, we know if we were making this, this would be the anode is the silver, so this would be a solid piece of silver in Ag plus solution. This would be a solid piece of gold in Au3 plus solution. We have our voltmeter here. Connect the wire. We know the electrons would flow this direction. And we have to have our salt bridge here. And we have our salt bridge. And we remember that our cell diagram starts at the solid anode, Ag solid, phase change to Ag plus, aqueous, salt bridge, 2 lines for salt bridge, Au3 plus aqueous, and finally Au solid. Boom. Got it done. All right, so that's how you would work out this type of reaction. And I could also have asked a question. It would take a lot more time, so I wouldn't write it on exam. I could say, you want a cell that gives you 1.4 volts of electricity. What cell would you use? That'd take a while, but you'd have to go through these potentials and find out, okay, find a reduction potential, make one of these an oxidation potential by flipping it and figuring out how you can get 1.4 volts. There's probably a number of different ways you could do it. It'd be a fun homework problem, but not a fun exam problem because there's just too much going on. All right. Another example problem that you can do with these reduction potentials looks like this. Say you have Br2 liquid and you add it to a solution of sodium chloride and sodium iodide at 25 degrees Celsius. What's going to happen? All right. So, all right, I've got bromine liquid, I've got sodium chloride, I've got sodium iodide. So the first thing to ask is, okay, what's all in solution? What all is in there? Well, we have Br2 liquid, we have sodium, Br2 liquid, Na plus ions, I minus ions, and Cl minus ions. Yes, because we got sodium chloride and sodium iodide, Br2 liquid, sodium ions, iodide ions, chloride ions. Well, what's going to react spontaneously with what? Well, we need to go to the table and look to see what is to the right of, or to the right and below other things. So let's take a look. I like to start on the right, and I'm looking at F2. Well, that's none of this. AU, PB, Cl2. Nope, I don't have Cl2. I have Cl ions, Cl anions. Well, here's Cl anions over here. Ooh, which means the only thing that's going to react with a chloride anion has got to be something up here, and I don't have any of that stuff. Okay, keep going down. O2, manganese, oh, here's bromine liquid, Br2 liquid. It's right here, which means I know what's going to react with bromine liquid, anything to the right and below it. Okay, so here's my bromine liquid. What's to the right and below it? Br, blah, 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 G, F, E, don't have any. Oh, here's iodide. I know that if I've got iodide now and bromine liquid, that bromine liquid will react with I minus because that's to the right and below it. The bromine liquid would become bromide ions. The iodide ions will become I2 solid. I know that reaction is going to happen. So, cool. I'm still looking though, is there any chloride or sodium ions over here? Chloride, Cl minus or Na plus over here? Cl minus, Na plus. I'm going down here, and it turns out, no. Ooh, but if we go way to the bottom, we find out we have Na solid down here. Is that can do anything? No, because I'm not looking for Na solid, I'm looking for Na plus. Na plus is below Br2, but it's not to the below and to the right. Well, here's my Na plus, though. Is anything that's in solution to the right and below it? No, nothing. All right. Also note, you might be worried, well, what about water? Don't we have water in there? Yes, we do, but if you look here, we see water is way up here, so the only thing that's going to react with water, if it's on the right, is something above it to the left, and we don't have any of that, so we don't have to worry about the water either. So we've found out through this table the only thing that will react is the bromine liquid will react with the iodide. And so that will give us these two reactions that we already looked at. And bromine liquid, what does it mean? It means bromine liquid is a strong enough oxidizing agent to oxidize our 2I minus into I2, but it's not strong enough to oxidize 2 Cl minuses to Cl2, and nothing strong enough to reduce Na to Na plus, nothing strong enough to reduce sodium ions into Na. At this point, you're thinking, oh, this is cool, but that math was just like addition and subtraction. Can't we get into better math? Can't we look at how redox reactions deal with delta G? Because we're talking about spontaneous reactions. Good deal. That's our next thing. More equations and more calculations using delta G.